Hello everyone, welcome to the lecture series on basics of electrical engineering. In this video, we're going to do some worked examples on series resonance. So, in case you're not subscribed to our channel, subscribe to it. Only then you'll be getting regular updates with respect to the videos that we post. All right, let's get started. Before starting the problems, we need to understand what are the important formulas that are associated with series resonance. And for these formulas, you need to know what is the theory behind series resonance. We cannot directly only remember the formulas. We need to have a logic behind why these formulas are. So the theory of series resonance is done in one of our previous videos. The link will be provided in the description. In case you've not watched that, please do watch it. It will give you a clear picture of how the formulas can be applied and what are the essence of these formulas all about. So the resonant frequency is given by 1 by 2 pi root LC. The current at resonance has been given by V by Z, that is nothing but V by R. The impedance with respect to at resonance is basically only the resistance part, because the inductive reactance and the capacitive reactance will be equal at that point of time and will be only left out with the resistive element that is there in the circuit. So bandwidth has been given by R by L. So solving this with respect to frequency, you'll be getting R by 2 pi L. Very important formula, this one. And the quality factor is defined in this particular fashion. Already it was explained. So please make a note of all these formulas at a particular point. Again, quality factor can is derived, and this is our final expression. In case they give you the value of RLC, how do we substitute and find the value of Q naught? That is a big question. So we'll be solving in this particular fashion. And power factor at resonance is always equal to 1, because the circuit is resistive. As a result, we'll be saying it equal to be 1. So these are the basic formulas. Make a note of all these formulas. So problems related to this are very simple. It's actually substitution of all these formulas directly. So that's the only thing there. So we'll be solving 5 different problems, and all of them are of different types. After solving all these problems, trust me, you'll have greater amount of confidence in order to approach problems on series resonance. All right, let's get started. This is the first example. A series RLC circuit has the following parameters: R, L, and C is given. Compute the resonant frequency, bandwidth, lower cutoff frequency, upper cutoff frequencies of bandwidth. So we'll be having a specific approach with the problems that we solve. First step is to write the given data with respect to whatever is given. We'll make a note of them so that we will not make any mistakes with respect to substitution. So that's our clear idea all about. Step one is to determine the resonant frequency. So how do we do that? We know resonant frequency is given by F naught is equal to 1 by 2 pi root LC. Substitute the value of L and substitute the value of C, you'll be getting 159.15 Hertz. So it's basically a straightforward substitution. Second step is to determine the bandwidth. That is what is asked in our question. So bandwidth is given by the formula R by 2 pi L. So we know the value of R, we know the value of L, and we know the value of pi as well. So substitute the value, and we'll be getting it equal to be 159.15 Hertz. So once we get the bandwidth, we have to determine the lower cutoff frequency and upper cutoff frequency of the bandwidth, that is F1 and F2. So F1 is given as F0 minus bandwidth by 2, and substituting these values, you'll be getting 79.58 Hertz. And upper cutoff frequency is given as F2 is equal to F0 plus bandwidth by 2. So substitute these values, you'll be getting 238.73 Hertz. As I mentioned, it's basically a straightforward substitution of the formulas. So it's very important to make a note of the formulas with respect to the problems that we're solving. So this is how we'll be approaching these type of problems. We'll get into our next example, which is example 2. A series RLC circuit consists of R, L, and C. Those values are given, and the applied voltage to the circuit is also given, that is 100 volt. Find the resonant frequency, find Q at resonant frequency, calculate bandwidth of the circuit. So for resonant frequency, it's basically the same approach, isn't it? So we'll be writing the given data, and for resonant frequency, it's basically the same approach as we followed in our previous problem. If not is equal to 1 by 2 pi root LC, substitute the value of L and C, and you'll be getting 159.15 kilohertz. To determine Q at resonant frequency, we know that Q is given as 1 by R into root L by C. So very important formula, this one. So substitute the value of R, L, and C, you'll be getting 0.1. Our third step is to determine the bandwidth. So how do we find the bandwidth? We know the value of R and L, so we can use this formula, R by 2 pi L. So you'll be getting around 1591.55 Hertz. So basically a straightforward problem. Again, solving it with respect to formula substitution will give you the answers right away. So once this is done, we'll go into our next example. This question looks a little big, but nevertheless it's very simple. But it gives you a clear idea of some of the other factors as well with respect to the problems that we solve. So they've given the resistance value, they've given the inductance value, we know the capacitance, and they've given the supply. So find determine the following with respect to series resonance circuit. We'll be approaching each of them individually. So first step is to write the given data, and once that is done, we'll be determining the resonant frequency. As usual, we'll be using the same formula. F naught is equal to 1 by 2 pi root LC. We know the value of LNC. Substitute it, you'll be getting 56.3 hertz. So once this is done, our next step is to determine current. So all of these are associated with respect to resonance, isn't it? So when we're talking about resonance, even in case of a series RLC circuit, it will behave as a resistive network at resonance. So with respect to resonance, when we are talking, the current will be given as I naught is equal to V by R, because the impedance offered will only have the resistive element in the circuit. As a result, we'll be writing in this particular fashion. Substitute the value of V and substitute the value of R, you'll be getting 10 amps. Once this is found out, we know power by the basic definition that is derived from Ohm's law. P out is equal to I out square into R. Substitute the value of I out square, we know the value of R, you'll be getting 1000 watts. So our next step is to determine the power factor. Power factor at resonance for a series RLC circuit is always equal to 1. That is discussed in our theory portion as well. With respect to important formulas also we have discussed. So very important point and observation. So make a note of it. And once this is done, we'll be finding the voltage across resistor, inductor and capacitor. How do we do that? We know by Ohm's law V is equal to IR. Based on that, V at R out, that is basically the resistor that is used, is equal to R into I out. So 10 into 10, substituting, we'll be getting 100 volt. Similarly, we'll be doing it for inductance. So the reactance associated with inductance is inductive reactance XL naught, indicated over here. So we can write XL naught as to be equal to 2 pi FL. So F naught is the resonant frequency. All of these are at resonance. So we are talking with respect to resonant frequency. So substitute 2 pi and the value of the resonant frequency L and I naught, you'll be getting 707.5 volt. And once this is done, we will be applying the same approach for the voltage across the capacitance as well. You'll be getting a value of 707.5 volt. So very important observation, as we made sure this was explained in the theory portion as well. At resonance, obviously the voltage drop across the inductor and capacitor will be the same, because XC naught and XL naught will be equal, isn't it? So in case you find VL naught, you don't have to even calculate VC naught. We can directly conclude from that point. Just to apply the formula and show you these two are equal, I've done this in this method. That's it. So once this is done, we'll be finding the quality factor. So how do we find the quality factor? Quality factor is given by Q is equal to 1 by R into root LC. We know the value of R, L and C. Substitute, you'll be getting it to be equal to 7.07. And then our step 7 is to determine half power points. So what is half power points? It is basically the lower cutoff frequency and upper cutoff frequency. Why it is called as half power points? With respect to definition of bandwidth, I told the bandwidth is defined with respect to the amount of power transferred, at least greater than half of the power that is to be transferred at a particular point in time. So that is always associated with half of the greater power. As a result, it's written as half power points. It can be twisted in this particular fashion. In order to determine the cutoff frequencies, they can ask you as half power points. So we'll pretty much apply the same formula with respect to the first problem that we have solved. F1 is equal to F naught minus 1 R by 4 pi L. Substitute the values of these, you'll be getting 52.32 hertz. Again, F2 is equal to F naught plus R by 4 pi L. Substitute, you'll be getting 60.3 hertz. So our final step is to draw the phasor diagram at resonance. So how does it look like? We basically saw this waveform in the theoretical portion as well. So this is the nature of I with respect to V, and the phasor diagram is V in phase with respect to I, because it is acting as a resistive network when resonance occurs in case of a series RLC circuit. As a result, V and I are in phase, and hence it is represented in this particular fashion. I hope this problem is understood and it gives you a clear overview of how to approach these type of problems. So we'll go into our next problem, that is example 4. They're given as a series RLC circuit. They have given the voltage. If the maximum peak voltage across the capacitor, they have given maximum peak voltage across capacitor as well. Find the quality factor of the circuit. So this problem is very straightforward. Just try to do it on your own by pausing this video at this point in time. In case you are not able to solve, nevertheless you will be able to understand by this approach. So They've given us Vm, Vcm is also given. Vm is basically observed from this equation. So V of t is represented as Vm sin omega t, isn't it? So Vm is basically 10 volt and Vcm is equal to 400 volt. So that is what they have given. Now we have to find the quality factor. How do we find the quality factor? In our important formulas, I defined quality factor with respect to three different equations, isn't it? We'll be using one of them. Q is equal to Vc naught by V. So Vc naught is basically the voltage that is across the capacitor, and V is the voltage across the main supply voltage that is associated with. So these are basically RMS value. So we have to determine the RMS value. V is equal to Vm by root 2 is the RMS value of the supply voltage, and that is given by 10 by root 2. 5 root 2 will be getting if we simplify. Again, Vc naught is equal to Vcm by root 2. RMS value is given by dividing it by root 2, and 400 divided by root 2 you'll be getting 200 root 2. Substitute both of these in Vc naught and as V in quality factor formula, you will be getting 40. So quality factor for this particular circuit is 40. So this is how we'll be approaching these type of problems. It is not that Q is equal to 1 by R into root LC will be used in every application of the problems with respect to quality factor. There might be problems suitably given with respect to only this data. So based on that, we will have to apply those formulas. So once this is done, we'll move on to our next problem, which is the last one. Example 5, a series RLC circuit is connected to 200 volt AC supply. The given the current drawn at resonance to be equal to 20 amps. The voltage drop across capacitor is 5000 volt. Calculate resistance inductance of the capacitor if the capacitance is 4 microfarad. Also calculate resonant frequency. So this looks slightly different. We have not solved this nature of problem previously, so please pay attention towards it. They've given us V I naught, Vc naught. They've also given us the capacitance value to be equal to 4 microfarad. Our first step is to determine the resistance. How do we do it? We know the current, we know the voltage, so it's basically the application of Ohm's law. R is equal to V by I naught. Substitute, you'll be getting 10 ohms. Very simple, isn't it? The first step is very simple. Second step is to find the inductance if they're given the capacitance value, and then find the resonance frequency as well. So we will be finding the resonant frequency at the first place. So Xc naught is given by 1 by 2 pi f naught into C. So Xc naught is given as Vc naught by I naught, isn't it, from Ohm's law? So substituting for Vc naught and I naught, because we know Vc naught, so substitute, you will be getting 250 ohms. Now what we'll be doing, we will be substituting this value over here so that we can find the value of f naught. You'll be getting f naught to be equal to 159.15 hertz. So once we have found resonant frequency, inductance can be found out easily, isn't it? How do we find that? We know at resonance Xc naught is equal to XL naught. So we'll be taking XL naught to be equal to 250 ohms. So XL is equal to 2 pi FL. So based on that, XL naught is equal to 2 pi F naught into L. Now substitute the value of all of these and you can find the value of L, and L will be given to be equal to 0.25 Henry. So this is how we solve problems related to series RLC resonance circuits. So in case you have any questions, feel free to reach out. So if you like this video, please do like it, share it, and subscribe to our channel for regular updates. Thanks for watching this video. Please do keep supporting. Thank you.